Hi again. Welcome to the network video on distinguishing between the various ways to move through a network, such as walks, paths and other approaches. Distinguishing amongst the various ways increases our ability to analyse interconnections more completely and identify what our networks can reveal about the complexity of a problem. Let's start by giving you a little map of part of my place. When I got out of bed this morning, I walked to the kitchen and then to the fish tank to feed the fish. Then I went back to the kitchen. Then I went across to the TV to turn it on so I could get some news and sports results. Then I went back to the kitchen to start making some coffee. Then I went to the video room to turn the computer on. Back to the kitchen as the coffee was ready. I then had to go back to the video to press enter on the computer. Damn it. Back to the kitchen to finish off the coffee. I went then back to the bedroom. From there I went back to the video room. Then I had to go to the TV and turn it off. And now I'm back in the video room, obviously. I'm exhausted, but I won't take the edge back to the bedroom until about 10 o'clock tonight. So the diagram shows I have 5 vertices, but I visited the kitchen 4 times, the bedroom twice, the TV twice and the video room 3 times. Even though there are only 6 distinct edges, I actually walked along 13 edges by duplicating 4 of them. When you move between vertices in this half-asleep way by duplicating vertices and edges, it's called a walk. We can take any route along any edge and through any number of vertices in the network. In a walk, we can use any vertex and any edge as many times as we wish. Now, if I plan my walk, I can save a fair bit of effort. I could, for example, go from the bedroom to the video room, to the fish tank, to the kitchen, and then back to the video place. In this diagram, I can use 4 vertices, and I walked along only 4 edges. I didn't need the TV, I had the news. All the edges were different. I started in the bedroom and finished in the video room. I visited each of the edges only once. The TV vertex was not relevant here, and therefore the walk has been refined. This type of network is now called a trail. In a trail, those edges which are used are only used once. A different trail would have been to go from the bedroom to the kitchen, to the TV, across to the fish tank, and then into the video room. All edges again only used once. I can also follow another trail. I could go from the bedroom to the kitchen, to the fish tank, to the video making place, to the TV, and later on back to bed. So I've shown that in green. The edges in this network are all only used once, so it's a proper trail. The difference is that I started and finished in bed. Very nice. That refines the concept of a trail further. Any trail that starts and finishes at the same vertex is now called a circuit. Now the trail and the circuit have emphasised no revisited edges. So our attention now turns to the presence or absence of revisited vertices. And we define a path as having no revisited vertices. The diagram I've got here represents a network which we can describe as a path. It goes from the bedroom to the kitchen to the TV to the video room. So there's no revisited vertices. So that network can be described as a path. Of course, it is also a trail because there's no revisited edges, but we keep the description as a path as it has the additional property. If we now put a link between the video room and the kitchen, then we have duplicated the vertex of the kitchen, so that takes it away from being a path and it restricts the definition to a trail. We could easily say that all paths are necessarily trails, but not all trails are necessarily paths. To refine further, if we take out that video kitchen link and add a link instead between the video and the bed, which is quite a likely edge tonight, it produces the same start and finish vertex. When we have a path with the same start and finish vertex, that is called a cycle. Finally, if we go back to our basic path that we talked about, which I'm showing again there, we can call a network connected if each pair of vertices is connected by a path. Well, the bed to kitchen, kitchen to TV and so forth, that's their paths. But the network here is connected because there is even a path between the bedroom and the video, admittedly via the kitchen and the TV. But the front balcony is not connected to any of the vertices that we have included. And because it's not connected, the balcony creates a disconnected network. So much to remember and so many definitions. So let's try to put it into some sort of a framework to make it easier for me and for you to be able to remember it. So we can have a little table where we've got vertices and edges, and we know that we're talking about repeating and not repeating. So if we have edges which are repeating and vertices which are repeating, we have a walk, basic. If we have the edges not repeating, then we either have a trail or a circuit. So put them down there, and there's a red E for edges and a red T for trail. We'll come back to that. Now, if the vertices are not going to be repeated, and therefore the edges are not going to be repeated, we can have either a path or a cycle. So we've got to get those around the correct way. And we go back to the red letters, ET. Who is ET? The guy who's got a message for you. So ET really stands for edges are unique in a trail. And we've got blue letters for vertices and path. So we can say that vertices are unique in a path. Silly little way to do it, but at least it gets you the message, and you just have to say that to yourself when you're doing exercises or in the exam. ET, VP. Just a comment about the work of a great Swiss mathematician, Leonhard Euler, who lived in the 1700s. He was a major force in the development of infinitesimal calculus, but also in graph theory or network theory. Euler regarded a graph, that is a network, as comprising nodes, edges, and regions. In other words, the areas inside or outside the edges. Amongst all sorts of other things he did, Euler identified two special yet related types of networks. Both types have the special characteristic in that they visit every edge of a network only once. We have two different sorts of Eulerian networks. One is the Eulerian trail, the other is the Eulerian circuit, and they use the definitions that we provided earlier. The Eulerian trail has two vertices of odd degree, and the trail starts at one odd vertex and finishes at the other. The Eulerian circuit has all vertices of even degree, and it starts and finishes at the same vertex. The importance of the Eulerian networks becomes clear when we might be planning a trip, for example, or we want to do some letterbox deliveries, and we only want to go along any road, or that is any edge, only once. Example. In this diagram, we have three vertices of degree 2, B, E and D, and we have two vertices of degree 3, A and C. The network is therefore going to be an Eulerian trail because we've got these two vertices of degree 3. Each edge can be used once and that's all. There are two possible trails because remember the trails have to start either at A or C. So therefore we're going to go A, B, C, AE, DC. We're going from one odd vertex to the other. You can do the one yourself starting from C. In the second diagram, we have 5 vertices, each of degree 2, and for interest, we have 6 edges. The network is therefore an Eulerian circuit because each of the vertices have degree of 2. The circuit can start anywhere and finish at the starting point. So one possible path is simply A, B, C, D, E, and then back to A. In summary, networks are analysed in terms of their vertices and edges and the number of times in a network they might be visited. There is a range of possibilities, and the terms used to describe networks are summarised on the website. Special networks using every edge were identified by Euler, and these are also on the website. In this video, we have established the basic concepts for understanding different types of networks. In the next video, we're going to analyse trees and spanning trees. Consolidate what you've learned here by doing the test yourself questions on the website, drjsmaths.com. Hit the like button and subscribe if you haven't already, then you'll get notifications about new videos. Good luck, see you on another network video.